Namaskar friends. Today we will study about plastic limit analysis. In plastic limit analysis, we are interested to find the ultimate load that would act on the system during the collapse of the system. When the system actually fails experiencing plastic deformations. Up till now, we have been discussing about linearly elastic material behavior. Linearly elastic material behavior means stress is directly proportional to strain, and the behavior between stress and strain is linear. It would be very unrealistic if we extrapolate the elastic solution into the inelastic range, that is the plastic range. When a structure collapses, the behavior of a structure is a plastic behavior in which the structure experiences large deformations which are unbounded and against certain loads. So, in the plastic limit state, the deformations are very large. And we are interested to find out what is the ultimate load corresponding to that particular situation. On your screen, there is a graph between, on the x-axis is curvature, ratio of curvature divided by curvature at the yield point, and on the y-axis is moment divided by yield point moment. Now this graph, you can see, this graph approaches MP by MYP when the curvature ratio is very large, and it tends to become stable at MP by MYP, although the curvature ratio is increasing and is very large. So there is a limit to moment which the structure experiences during plastic deformation. And that limiting moment is the plastic moment MP. The structure cannot experience more moment than this, although the deformations are large. So there is a limiting moment against which the structure deforms plastically and experiences large deformations. So you can see that a rather constant plastic moment MP is achieved and rather maintained during plastic deformation. And a rather abrupt transition from elastic to ideally plastic behavior occurs at MP. Now we'll introduce here the concept of plastic hinge. Plastic hinge is a hinge which allows large rotations to occur, and at the same time, on the plastic hinge, there is a constant plastic moment MP. So this is a typical type of a special type of hinge where large rotations are possible at constant plastic moment. Of course, now in plastic limit analysis, elastic displacements are neglected because plastic displacements are much larger than the elastic displacements. When uh, structure deforms plastically, the structure uh, deforms in a mechanism of collapse, and that mechanism of collapse is called a collapse mechanism. So collapse mechanism is a mechanism which the structure adopts while deforming plastically. So to find now in this plastic limit analysis, we have also to uh, propose or to find a collapse mechanism for the structure. And this is done by inserting a plastic hinge or hinges in the structure. And insertion of plastic hinge or hinges in the structure allows us to propose a kinematic mechanism which permits large unbounded displacements of the system. So plastic mechanism is obtained by inserting plastic hinge or hinges, and this allows us to get a kinematic mechanism which can experience unbounded displacements of the system. And this kinematic mechanism should be plausible. That means it must be admissible. That means it must be achievable. There are two methods for plastic limit analysis. One is based on conventional statics, and it is called equilibrium method. And the other method is based on the principle of virtual work. One thing we have to keep in mind that during plastic deformation and while doing the plastic limit analysis, bending moments anywhere cannot exceed the plastic moment MP. The maximum moment which the structure can experience in a typical collapse mechanism is MP. Okay, let's now try to understand with one example. So in our screen, there is a simply supported beam. This beam is experiencing a central load of capital P. And we have to find out the limiting load, plastic limit load for this structure. On the right side, there is a collapse mechanism which has been suggested. The load corresponding to the collapse mechanism is P subscript ULT, P ultimate. Now this is the maximum load which the structure can take. And you can please see the mechanism. In this mechanism, we have introduced from our side a hinge at the center of the beam. So introduction of hinge at the middle of the beam allows us to propose a collapse mechanism which we are seeing on the right side of our screen. You can see the left end of the beam in collapse mechanism has deformed by delta theta. Right hand also has uh, deformed angularly by angle delta theta, and the plastic hinge in the middle of the beam has experienced angular deformation of 2 delta theta. Below the schematic of the simply supported beam, we have drawn bending moment diagram. There are two bending moment diagrams. One is dotted and one is continuous. The dotted bending moment diagram is corresponding to yield point moment MYP, and continuous bending moment diagram is corresponding to the moment MP at the plastic limit of the structure. Clearly, MP is greater than M by P, and MP as well as M by P are occurring exactly at the middle of the beam. Now let us look at the curvature diagram also. The curvature diagram of this structure is drawn below the collapse mechanism. The dotted curvature diagram is corresponding to yield point moment, and the continuous curvature diagram is corresponding to plastic moment. And we can see that during plastic deformation, the curvature at the plastic hinge which we have introduced has become very large. Now, when the moment is MYP at middle of the beam, then we can equate that moment to PL by 4. And from there we can obtain the yield point load PYP equal to 4 MYP by L. This we have obtained simply by equating the moment at the middle of the beam to the yield point moment. In similar fashion, ultimate load can be obtained by setting plastic moment MP equal to PL by 4. So that gives P ultimate equal to 4 MP by L. Please remember PL by 4 is the moment at the middle of the beam. Now using equation 1 and 2, we can very easily arrive at P ultimate equal to MP by MYP into PYP, where MP by MYP is called a shape factor K. So you can write P ultimate equal to K PYP. And this ultimate load P ultimate is greater than the yield point load PYP by factor K. So the same problem we can also solve using the principle of virtual work. According to the principle of virtual work, external virtual work has to be equal to the internal virtual work. Now in this collapse mechanism, which is there on our screen, we can see that the external virtual work would be equal to the external load multiplied by the deformation in the direction of the external load. Now the external load in this case is P ultimate, and the deformation in the direction of the external load is delta triangle. So this gives us external virtual work as P ultimate into delta triangle. And delta triangle we can write here as L by 2 into delta theta. So that we have done. Delta triangle equal to L is equal to L into delta theta divided by 2. And here we can see, corresponding to this particular collapse mechanism, plastic moment MP would occur at this plastic hinge which we have introduced in the middle of the beam. There will be no plastic hinge at this, there will be no moment at this hinge, and also there will be no moment at this hinge because these ends are simply supported. But there will be a plastic moment in the middle of the beam which would act during the plastic deformation and which would remain constant. So the internal virtual work becomes MP into 2 delta theta. So here we have MP into 2 delta theta. And from here we can find out P ultimate equal to 4 MP by L, which we had also arrived at using equilibrium method, that P ultimate equal to 4 MP by L. So here we can see that the ultimate load is directly proportional to the plastic moment, and it's inversely proportional to the length of the beam. Okay, now let us determine plastic limit load for this particular structure. So here we have a beam of length capital L. On the left side, this beam is fixed, and on the right side, this beam is simply supported. And there is a central load of capital P, which is acting at the middle of the beam. We want to find out the ultimate load which this beam can experience. That is the plastic limit load. Now, to find out this, first of all, we need to solve the reactions of this particular structure. That means we want to find out capital M, we want to find out capital P3, we want to find out capital P4. Capital M is the moment at the left end of this beam. Capital P3 is reaction at the left end, and capital P4 is vertical reaction at the right end. This structure is indeterminate to first degree. A first order indeterminacy is there. Now let us use displacement method of elastic analysis to find out the reactions capital M, capital P3, and capital P4. Please recall that in displacement method, we assume as if this particular configuration of the structure is made up of two configurations. That means when two configurations are summed up, superimposed, then this particular configuration is arrived at. So the two configurations are, in the first configuration, we have fixed the right end. You can see in this below this beam, we have made another beam in which right end is also fixed. And now here in this structure, the unknowns are capital M1, capital M2, which are the moments on the two ends, and vertical reactions capital P by 2 and capital P by 2 on both the ends. Clearly, this structure is statically determinate. And the other configuration which we will assume is this one, in which the external load capital P has not been considered now, and we have given a rotation theta to the right end. Okay, let us first of all consider this configuration, and let us consider a section at distance x from the left end. For this particular section, we can write EI d square v by dx square equal to p by 2x minus m1. Integrated, we have EI dv by dx equal to px square by 4 minus m1x plus c1. Again integrated, we have EIV equal to px cubed by 12 minus m1x square by 2 plus c1x plus c2. Now, if we apply the boundary conditions that at x equal to 0, deflection is 0, and also at x equal to 0, slope is 0, then we find that C1 equal to C2 equal to 0. And at x equal to L by 2, we can see this that the slope of this particular system would be 0. So 0 equal to PL square by 16 minus M1 L by 2, and this gives us capital M1 equal to PL by 8. So we have solved this particular beam, and here in this case capital M1 would be equal to PL by 8, and due to symmetry M1 would be equal to M2 and M2 would also be equal to capital PL by 8. Now let us look at this configuration. Now our job is to find out capital M3, capital M4, capital P1 and capital P2 in this particular configuration. In this configuration, please appreciate that we have not considered the external load capital P. That has not to be considered. So here, if we consider a section at distance x from left end of the beam, then we can write EI d square V by dx square equal to P1 x minus M3. Integrated again, we have EI dV by dx equal to P1 x square by 2 minus M3x plus C1. Again integrated, we have EIV equal to P1 x cubed by 6 minus M3x square by 2 plus C1x plus C2. And if we apply the boundary conditions that at x equal to 0, deflection is 0, and at x equal to 0, slope is also equal to 0, we get C1 equal to C2 equal to 0. And now here the boundary condition is that at x equal to L, slope is theta. So we have, before that, at x equal to L, deflection is also 0. So that gives 0 equal to P1 L cubed by 6 minus M3 L square by 2. And we get capital M3 equal to P1 L by 3. And M4 equal to P1L minus P1L by 3. That means 2P1L by 3. Right? So we have expression of capital M3 and capital M4 in terms of P1. Now, at x equal to L, slope is theta. That gives us EI theta equal to P1L square by 2 minus M3L. And from here, we can find out capital P1 equal to EI theta divided by L square. And M4 equal to 2P1L by 3. And we can find out that capital M4 equal to 4 EI theta by L. Now, we will argue that this particular configuration is the original configuration, and this configuration is obtained when we add this particular configuration to this particular configuration. So now we will argue that this is the original configuration, and in this original configuration, moment at right end is 0. That means M2, which is moment at right end of this particular configuration, plus M4, which is moment at right end of this particular configuration, should be equal to 0. So for moment equilibrium at right end of the original beam, minus 4 EI theta by L plus PL by 8 has to be equal to 0, where M4 is 4 ei theta by L and M3 is P1L by 3. And M2 we have found out is PL by 8. M4 is 2PL by 3, 2P1L by 3. And here M4 equal to 2P1L by 3 equal to 4 ei theta by L. So minus 4 ei theta by L plus PL by 8 equal to 0. That gives theta equal to PL square by 32 ei. Right? So this gives, now this gives us the value of theta. But we are interested in finding out how much would be this capital M, which is the bending moment at the left end of the original beam. And this bending moment at the left end of the original beam is equal to M1, which is bending moment at left end of this configuration, plus M3, which is bending moment at left end of this particular configuration. So now capital M equal to M1 plus M3 equal to minus PL by 8 minus P1L by 3. So substituting the value of P1, which we had derived 6 ei theta by L square, and also putting the value of theta, we get capital M equal to minus 3 by 16 into capital P into capital L. Also, capital P3, that is a reaction at the left end of the original configuration, is equal to P by 2, which is a reaction at the left end of this configuration, plus capital P1, which is vertical reaction at the left end of this particular configuration. And that gives us capital P3 equal to P by 2 plus P1, that is equal to P by 2 plus 6 ei theta by L square. And that gives us capital P3 equal to 11P by 16. And from here we can find out P4. P4 is vertical reaction on the right end of this particular configuration. We can clearly see P4 equal to capital P minus P3. Now P3 we have already obtained, so capital P4 now becomes capital P minus 11 by 16P, and that is 5 by 16 capital P. Okay, now we have completely solved the problem. This particular configuration we have now completely solved. That means we completely know the value of capital M, we know the value of capital P3, we know the value of capital P4. And what are the values which we have just derived is bending moment at the left end is minus 3pl by 16. Reaction at left end is 11p by 16. And reaction at right end is 5 capital P by 16. Now let us try to find out the plastic limit load. Please see that at x equal to capital L by 2, the bending moment would be 11 PL divided by 32 minus 3PL by 16, where 3PL by 16 is the bending moment at the left end. And that gives us capital P equal to 5 by 32 PL. Now we are ready to draw the bending moment diagram for this particular configuration, because we know bending moment at the left end is minus 3PL by 16. Bending moment at the middle we have just derived, and we know that the bending moment at the right end is 0. And also we know the bending moment would linearly vary from this point to this point, and also linearly vary from this point to this point. So from these three points, we can find out the bending moment diagram by simply joining linearly. So at left end, we have drawn a vertical line minus 3PL by 16. At the center, we have drawn point I, which is away from this horizontal line by 5PL by 32. So joining these points, joining point F and I and joining point I and H, we have the bending moment diagram. In this bending moment diagram, there is a dotted line also which has joined point F and point H. And on this dotted line, there is a point G, which is vertically down point J. And we can see that IJ plus JG, that is 5 by 32 PL plus 3 by 32 PL. This distance JG equal to 3 PL by 32 can be obtained by observing that triangle EHF. Triangle EHF. EHF is similar to triangle JHG. Now, now we can set the elastic moment equal to MYP, the maximum elastic moment. The maximum elastic moment in this particular bending moment diagram we can see is at the left end, and which is 3PL by 16. So we get the elastic load, maximum elastic load, or the yield point load as 16 MYP by 3L. Let us look at the same diagram again. We have drawn the same diagram again, but here we have used the concept of plastic limit analysis. According to the plastic limit analysis, the maximum moment which can occur in the structure is yield point, is the plastic moment MP. So you can see moment at the left end, that is E dash F dash, is MP, and the moment at the center I dash J dash is again MP. Now we have joined point F dash and H dash by a dotted line, and G dash is a point on the dotted line vertically below point J dash. You can see here that so there is one mistake here. this is I dash, here I have written I dash G dash equal to MP by 2. Actually, it should be J dash G dash equal to MP by 2. Uh, J dash, this is J dash, G dash, this is MP by 2. And this we can see from observing that triangle E dash, H dash, F dash is similar to triangle J dash, H dash, G dash. And from here we can write I dash J dash plus J dash G dash. That is I dash J dash plus J dash G dash equal to MP plus MP by 2. And this is equal to the ultimate moment, which is P ultimate into L by 4. So from here, we can find the ultimate moment as 6 MP by L. And yield point moment we had already derived as 16 MYP by 3L. From the expression of ultimate load, plastic limit load, and the yield point load, we can see that we can now write 3 PYP by 16 MYP equal to P ultimate by 6 MP. And from this expression, the P ultimate comes out to be 9 by 8 MP by MYP into PYP. And if we write MP by MYP as K, so we have 9 by 8 K into PYP, where K is called the shape vector. So the same result we can now find out using the virtual work method also. Now let us see how we can nicely use a virtual work method to find out the plastic limit load. Okay. This is the collapse mechanism. As we can recall that to find out the plastic limit load using the method of virtual work, first of all, we have to think of a collapse mechanism. We have to propose a collapse mechanism. So we have proposed a collapse mechanism by introduction of two hinges. One hinge we have introduced at the left end of the beam, and another hinge we have introduced at the center of the beam. One hinge is here, one hinge is here. This hinge was already there because it is free to rotate at this point. The slopes are allowed here. This hinge we have introduced at the location of maximum moment, and this hinge also we have located at the location where the moment is high. When plastic deformation occurs, when collapse mechanism is realized, the moment anywhere in the structure cannot be more than the plastic moment MP. So the maximum moment which exists in the structure during collapse mechanism is MP. Now let us use the principle of virtual work, which says external virtual work at the plastic limit is equal to the internal virtual work. Now external virtual work in this particular case would be P ultimate, which is the external load, into delta triangle. So P ultimate into delta triangle, that is equal to the internal virtual work, which is MP into delta theta plus MP into 2 delta theta, where MP into delta theta is work which is done due to rotation against plastic moment MP at this end, and which is MP delta theta. And MP2 delta theta is the work which is done due to plastic rotation about this hinge against plastic moment MP. So the work here in this particular case, internal virtual work would be MP into 2 delta theta. Total internal virtual work would be MP into delta theta plus MP into 2 delta theta. So we have P ultimate delta triangle equal to MP into delta theta plus MP into 2 delta theta, and this gives us ultimate load as P ultimate equal to 6 MP by L. So we had derived this ultimate load using uh, equilibrium method, and also we have derived this ultimate load using principle of virtual work.